Hi everyone, this is Huihan. Today I will be presenting our work, Runtime Monitoring with Interactive Imitation Learning, a joint work with Shivin, Roberto, and Yuke. We have seen significant development of robot learning methods in recent years, achieving impressive results in research settings. However, robots today still fall short of generalization and robustness for robust deployment in the wild. How can we reliably deploy learning-enabled robots to real-world tasks? To ensure safe and reliable deployment, interactive imitation learning employ the human to supervise the robot deployment and provide help when the robot makes a mistake. While promising, existing methods often require constant human supervision, incurring high human workload. Our key idea is to develop a runtime monitoring algorithm that continuously learns to predict errors from deployment data. We illustrate how the runtime monitoring works in operation. The robot inserts a coffee pot into the coffee pot holder. At first, the robot performs the task autonomously. Then the robot gets stuck. The system predicts an error and asks a human for help. The human comes in to provide intervention, and the robot can do the rest of the task autonomously again. With this, we present serious runtime monitoring, a model-based runtime monitoring algorithm that uses data at deployment to train the error predictors. During deployment, the robot performs autonomous execution until the algorithm predicts an error and asks human for help. The human chooses when to intervene. These data are used for training, where the rollouts and the human interventions are used for the model update. Both the policy and error predictor are updated, and their updated version are then deployed again. We now present two key ideas that enable this design. Our first key idea is to adopt a model-based approach to enable future error prediction. We would like the runtime monitoring algorithm to preempt potential errors in the future. To do this, we learn a latent space dynamics model that simulates future action outcomes. The dynamics model takes in the current state and the current action and output the next state. It does this iteratively to predict the future state in t-time steps. We encode the image observation into latent embeddings and train a latent space. On top of this latent space, we jointly train a policy head that predicts the policy action given the embedding. We also train a failure classifier that predicts whether an embedding represents a failure state. The joint training of the dynamics and the policy enables the model to perform rollouts into the future. Once we simulate into the future, we can see if the future state is a normal state or an error state. We classify two scenarios as errors. First, failure detection. Second, out-of-distribution detection. A state is a failure if it is classified as a failure by the failure classifier. A state is out of distribution if the distance to the nearest neighbor is the in-distribution embeddings is above a threshold. Our second key idea is that human interventions can tell us when the robot will fail and can be used as failure labels. Take this as an example. The robot tries to grasp the gear and fails, and the human intervenes. We note that the states before human intervention are abnormal states that should be avoided. We use these states as failure examples that reflects the human's risk assessment and trust for the robot. The normal rollouts and abnormal states before each human intervention are used as normal and failure labels and can be used to train the failure classifier. We use full human supervision initially to bootstrap the failure classifier, which give initial human intervention labels. As the robot improves its autonomy during deployment, the human-robot interaction evolves. Consequently, the failure labels are continuously updated to refine the error predictor, aligning it with the changing human risk assessments. We evaluate our serious runtime monitoring system on 4 tasks: nut assembly, threading, coffee pot packing, and gear assembly. We evaluate the combined policy performance of our human-robot teaming system under runtime monitoring. Our robot-human system keeps improving over deployment rounds, outperforming the baselines. We also evaluate whether the runtime monitoring system makes efficient use of human workload during deployment. Intuitively, we want the system to engage the human operator precisely when it is the most necessary. We measure the return of human effort inspired by our prior work, Fleet Dagger. This measures the ratio of policy performance over human workload. The policy performance is formulated as the expected return of the policy, and the human workload-human intervention ratio. The increasing return of human effort plot shows that our runtime monitoring system makes more efficient use of human workload during deployment. We also show the qualitative performance of the runtime monitoring system in operation. The green filter here indicates the moments where the runtime monitor detects an error. As we can see, it is able to capture different modes of failures, for example, getting stuck at insertion, aiming at the inaccurate position, getting stuck at insertion for a different gear, and failing to grasp the gear. In summary, we present a runtime monitoring mechanism that predicts errors from deployment data. It is able to perform continual update of error predictor in long-term deployment. The algorithm uses a model-based approach for future outcome prediction. The error prediction is intervention-informed that reflects human risk assessment and trust for the robot. Please check out our website for more details. Thank you.